So we have integral, definite integral of x upon a square cos square x plus b square sin square x within the limits 0 and pi, lower limit being 0, upper limit being pi. Now here, if we can see there is an algebraic function x here, and in the denominator we have trigonometric functions. In particular, when we have x in the numerator, the sixth property of definite integral is very helpful. So we apply the sixth property, according to which just need to replace the variable present in the integrand by upper limit minus the variable, provided the lower limit is 0 here. So for x, we can write pi minus of x, a square cos square, in place of x again pi minus x, plus b square sin square, in place of x we write pi minus x once again. Now cos of pi minus of x is minus cos x, but because of presence of square, that minus will be converted to plus, so we get cos square x back here. So a square cos square x and b square sin pi minus x is already sin x and its square is also there. So we get b square sin square x. So the numerator has been converted to pi minus x. This is the second equation. Now, as usual, if I add first and the second equations, what I get on the left hand side is I plus I, which is twice I. Right hand side integrals being under identical limits of integration. So when we add them, we can bring the integrands under a single integral sign. So this portion means x upon a square cos square x plus b square sin square x can be seen here in addition with this portion pi minus x upon a square cos square x plus b square sin square x with respect to x, right? Now you can observe the denominators, they are identical. So this portion becomes the common denominator or the LCM here. So a square cos square x plus b square sin square x is the LCM. Since the denominators are identical, so numerators will be added automatically. So we will be writing x plus pi minus of x, which we have written here. X and minus x gets cancelled. We have shown the cancellation work also. This pi being constant, you can bring it outside, place it here. So you're now left with twice of I on the left hand side, pi on the right hand side in product with definite integral within the limits 0 to pi. 1 is left over here, 1 upon a square cos square x plus b square sin square x with respect to the variable x. Now, here the most important thing you should take care of is when we deal with the same sum but within the indefinite integration, not for definite, we have the normal tendency of solving this question is to divide numerator as well as denominator by cos square of x. But in this case, note it very carefully that we cannot do that. Why? Because cos is something which assumes the value 0 between 0 and pi. If we are dividing by quantity, make sure that that quantity or that expression is not becoming 0 in between these two extreme limits. If it is becoming 0, you need to rework, you need to do something so as to modify the question and proceed further. Like for this one, I will say that you should restrict yourself from dividing by cos square x, otherwise this question will go wrong. So what exactly can be done? When we are dealing with definite integrals, the limits 0 to pi, they are not included. The endpoints of the limits, they are not included. So there is a rule according to the eighth property which enables us to convert the upper limit to its half, subject to the condition that f2a minus of x comes out as same as fx. So 0 to 2a fx dx can be written as 2 times 0 to a fx dx only if f2a minus x is equal to fx. And 2a is whatever we have as the upper limit. So in place of 2a we have pi here. So in place of x, if I write pi minus of x, this remains cos square x. Similar thing we have seen here in the denominator also. And b square sin square pi minus x again gives you sin square of x. So this property is satisfied. So this helps us in reducing the upper limit to its half. The 2 that we take common from here will be multiplied with the entire integral like this. So here we get twice of I as usual, the left hand side. 2 taken from the upper limit comes over here. Pi is already existing there. The upper limit, it's very important to note. Earlier it was pi, now it has been converted to pi by 2. So then you're left with 1 upon a square cos square x plus b square sin square x within the limits 0 to pi by 2. Now the most important thing to note over here is when we get 0 to pi by 2 as the limits of integration, we are allowed to divide numerator as well as denominator by cos the square of x. So here once the upper limit has been converted to its half, pi by 2, neither 0 nor pi by 2 is a part of this integral. You can say the limits, when we are talking about limits, neither 0 nor pi by 2 is included. It means x is not taking values as 0 and pi by 2. So now if we wish to divide numerator as well as denominator by cos square of x, we can do that. Why? Because there is no point between 0 and pi by 2 at which cos square x or simply cos x becomes 0. So if we divide numerator as well as denominator by cos square of x, we get 1 upon cos square x leading to secant square of x. A square cos square x divided by cos square x leads us to a square plus b square sin square x divided by cos square x makes it tan square x. Now the basic idea for performing integration by substitution is to look at the numerator and find out that function whose derivative is the numerator here. Now here we have secant square x as the numerator, and think of the function whose derivative is the numerator. Secant square x is the derivative of tan x, and we just look at the availability of that tan x over here within the integrand. Yes, tan x is available here. So we can go for tan x is equal to t. Differentiating, we get secant square x with dx is equal to dt. So this portion will be converted to dt, which is as good as 1 dt. A square remains as it is. B square remains. For tan x, we took it as t. So this becomes t. Tan square x becomes t square. So we get 1 upon a square, b square, t square. Remember, when we are converting from old limit to new limit, we have to make use of the link that we have established between the old and the new variables. So we have tan of x is equal to t. The lower limit of integration here is 0. This is with respect to x. So we feed x equal to 0 here. Tan of 0 makes it 0. So the modified new lower limit of with respect to the variable t is now 0. Now likewise, if I take x as pi by 2, feed it here, tan pi by 2 makes it infinity. This is something unusual, but it is very, very specific about this sum. Upper limit becomes infinity. Now we have a new integral. Now normally when we have an infinity sort of thing as the upper or the lower limit, we take it as something like u, and then we write limit u approaching infinity. But for Cbse, things can be taken lightly here. We are allowed to use infinity directly. So otherwise it becomes an improper integral here. Now we wish to apply a standard formula, something resembling like 1 upon x square plus a square. But x square plus a square is applicable when x square is coefficient 1. In place of x square, we have t square here. So we wish to get rid of this b square. So if I take b square as common, so this t square I'll prefer writing first. And this adjoining term will be divided by b square. We get a upon b whole square here. So this is the modified version. Now this can be compared with the standard formula integration of 1 upon x square plus a square. So indefinite integral has formula 1 over a tan inverse x by a. 1 over a. In place of a we have a by b, so we write a by b here. Tan inverse of, in place of x we have t, and in place of a we have a by b. So tan inverse x upon m is t divided by a by b, which can again be rewritten as tan inverse bt upon a. Now look at the limits of integration. We have 0 to infinity here. We can justify this b and b square. Single power will get cancelled. So we get pi upon ab here. Now tan inverse of, now in place of t, just feed the upper limit, which is infinity. Tan inverse, this will become infinity. Tan inverse of infinity means that angle on which when tan operates gives you the answer infinity, and that angle is pi upon 2. So we'll write pi by 2 over here. And from there we need to subtract tan inverse of 0. Tan inverse of 0 means that angle on which when tan operates gives us answer 0, and that angle is of course 0. So pi upon 2 minus 0 is what we are left with here. So it is pi by 2 here. Simply multiply, we have pi square divided by 2ab, and this becomes our final answer. So this is one of the most important sums. Over to question number 8.